next we have Dr. Phillip Jordan. Sorry, I'll just come back. So Phillip is a principal hydrologist with over 24 years experience. He works at Hydrology and Risk Consulting, HARC. The focus of his work is on modelling the impact of bushfires on long-term yields and forested catchments. He was also the project leader for e-water source catchment software, which he's used in multiple projects with his work both here and in New Zealand. He was also a fellow of the Peter Cullen Water and Environment Trust. So Dr. Phillip, if you would like to take over, that would be great.
Great, thank you. I'm assuming you can see my screen?
Yes.
Yes, great, fantastic. So I'm delighted to be here this afternoon to present to you on some work that myself and my colleagues at Sinclair Knight Mertz and then HARC, and then also several associates at the University of Melbourne have undertaken over the years on characterising the hydrological response of runoff from forested catchments to disturbances. So by disturbances, I'm really referring to three main causes of disturbance in forested catchments. The focus of today's talk, which is on bushfires, but that also interacts, and I'll get into this a bit later, with timber harvesting and the influences of climate change. So in outline today, I'm going to talk about the drivers of hydrological response in forested catchments, and that's the classic Kazira curve. And then I'm going to talk about three specific case studies. The first one looking at water yield from Melbourne's forested catchments. The second one looking at the long-term changes in water yield following bushfires that occurred in the Murray-Darling Basin in 2003, 2006 and 2009. And then the third case study is looking at changes in the short-term flood risk in the Thompson and Latrobe River catchment. The final area I'll talk about will be recent developments in modelling these sorts of impacts and in future directions. So firstly, drivers of response in forested catchments. About half of Melbourne's forested catchment area is covered by mountain ash forest and other ash species forests. So the remainder mainly being mixed species eucalypt forest or drier eucalypt forest. When the wetter ash forests are burnt by a high severity bushfire, the trees are all typically killed. And so what you get is this sort of response. So the 0 years showing a removal of all of the trees by an intense wildfire and an intense bushfire. After about 5 years, the trees start to come back and you get saplings growing, and they grow up over about a period of 20 to 30 years, which you can see there. After that point, the mountain ash forests or the ash-type forests tend to self-thin. So there's a reduction in the number of trees per hectare. And so what happens over time is that there's a change in both the leaf area index and the sapwood area index. And it's that change in leaf area index over time and the change in the amount of sapwood that affects the amount of water that is sucked up through the root system and transpired out of these mountain ash type forests. So what that looks like is described by the Kazira curve, which George Kazira derived back in the mid-1980s. And what that shows, as you can see here, is that there may be a small initial increase or possibly no increase in water yield in those first couple of years. But then as the forest grows back, the high density of new saplings causes a net reduction or net change in water yield compared with the mature forest. That peaks at somewhere between 20 and 30 years, but then the self-thinning effect kicks in, and there's a change in the water yield where the water yield gradually increases. And after about 150 years, we get back to a situation where the water yield from that forested catchment is back to its mature long-term state. The important thing to note is that this was derived only for ash forests, so reseeding type eucalypts. It was derived post the 1939 bushfires, which caused widespread devastation across Melbourne's water supply catchments. And it was derived using data that George had available to him at the time. So that was pre-fire streamflow data from 26 to 38, and then post-fire streamflow data from 1941 to 1981. Later, Matthew Brookhouse came back and looked at how those curves looked with some additional streamflow data that was collected over a longer period of time. And he found a very similar shape to the response, but with a little bit of an earlier peak, a slightly faster recovery, and a slightly lower peak than what George Kazira found. You can see, though, that even in George Kazira's original curves, there's a considerable degree of uncertainty in those water yield curves. Having said that, there's definitely a significant effect. So that peak reduction in water yield of somewhere between 400 and 600 millimetres a year obviously amounts to a significant amount of water across a forested catchment. So moving on to Melbourne's water supply catchments. They've been modelled over the years using a model that was developed by Fred Watson around in the late 90s and early 2000s called MCAC. MCAC's a very detailed model which cuts a forest catchment up into a number of hill slopes. The hill slopes then have many processes modelled, so the rainfall coming in, evapotranspiration coming out from the overstory and the understory canopy, and also directly from the soil. That then accumulates down the hill slope and adds up, once we add up all the hill slopes and we add up all the strips down the hill slope, we can get a derivation of the change in water yield over time. And that MCAC model can then be calibrated against gauge streamflow data. That was looked at in a study called the Wood and Water Study, which was conducted in the first decade of the 2000s. So Paul Fakemer and others derived a MCAC model for the Thompson catchment, and their model, their result which comes out of MCAC for the change in water yield over time is shown by the red curve. So we can see there that it's quite similar to the Kazira curve. It does show, MCAC model does show that there is a small period of a slight increase in water yield that persists for about 2 or 3 years after the bushfire. But then the same sort of peak reduction in yield of about 600 millimetres per year, and then a long and slow recovery back until the forest is about 150 to 250 years old. The Wood and Water Study and the modelling that was done by Paul Fakemer and others also looked at other species. So they were able to look at derivations of the change in water yield for other species types. And you can see that for Delegatensis and regnans, so the ash-type forests, there's a fairly similar response curve. And it's, again, similar in peak to the Kazira curve. However, for mixed species eucalypt forests, they found that there was the peak reduction in yield was smaller and the recovery was a bit faster. And again, and the same for silver wattle or for acacia. And the significance of that is that if it depends where the bushfire occurs, and it also affects the water yield can also be affected by what species might come back in place of a severely damaged forested ecosystem. So Paul Fakemer and others then also applied the MCAC model to look at the 2009 bushfire severity. It was limited or affected. The high severity fire was really in the catchments in the northern part. So Wattle and Silver Creeks was virtually completely burnt. There was also a significant area of high severity fire in the O'Shanassy and Maroondah catchments. But in the Upper Yarra, it basically didn't touch the Thompson or Upper Yarra catchments. So the net reduction, projected reduction in streamflow yield across Melbourne's system due to the 2009 bushfire predicted in their study was between 12 and 24 gigalitres per year. My second case study is looking at the Murray-Darling Basin. So Murray-Darling Basin, obviously high importance for irrigated agriculture and human habitation and water supply to Adelaide, and also environmental assets across the Murray-Darling Basin. So water yield is obviously very, very important. It's been subject to really 4 significant bushfires over the last couple of decades. So the 2003 alpine bushfires in Victoria burnt more than 1 million hectares, and that's shown in green. The grey area shows the area of the 2006-07 bushfire, which again burnt just over 1 million hectares. And then the 2009 Black Saturday bushfires burnt about 400,000 hectares, which did straddle the catchments flowing south towards Melbourne, but also the catchments that flow to the north and into the Murray-Darling Basin. And then I don't have it on this map, but obviously the bushfires that occurred over the recent summer affected a significant area of the Murray-Darling Basin. And the significance of that, as I said, is that this is really the highest yielding part of the basin. So if we look at mean annual runoff, all of those dark blue areas were really the areas that were affected by those bushfires. So 2003, rough spatial extent there, 06, 07 there, 2009 there. So based on some work that I did with some colleagues back at SKM several years ago, we looked at, we used a model called BISI, which is a much simpler computational structure than macaque, but it represents a lot of those similar structures that you see in a macaque model, or a lot of those, and also picked up by the Kazira curve, with that change in water yield over time, which depends on where the fire occurred, the age of the vegetation pre-fire, and the severity of the bushfire. So, for example, for the Dartmouth Dam catchment, which is one of probably the most significant storage in the southern Murray-Darling Basin, we can see that the BISI model shows a slight increase in runoff, all those green areas in that first year post-fire. But looking 25 years post-fire, you can see all of the red, pink, orange areas are the areas where the BISI model was predicting significant reductions in yield across the Dartmouth Dam catchment. So what that looks like when we accumulate it is that the black line is the response that we would have expected had there not been the 2003 bushfire. So a gradual recovery or gradual increase in yield as the forest that was there prior to 2003 continue to mature, get older, and therefore use gradually less and less water. The grey dotted dashed line shows the fire response. And it's really the gap between those two lines and then adding that up over time that adds up to the cumulative yield. So that cumulative yield is, I think my numbers are about 200 gigalitres over time, or about 10% of what we would consider sort of a current estimate of water yield into Dartmouth Dam. My third case study is really looking at the change in short-term flood risk in the Lower Thomson and Latrobe rivers. So in the Lower Thomson flood study, we had a RORB model, which is commonly used for flood estimation for the Thomson and Latrobe rivers. That was calibrated to a large number of streamflow gauges across the catchment, and then that was fed into a two-flow model to model the hydraulic impacts or the flood impacts in the lower part of the Thomson River. As a sensitivity run, there was a run done where a bushfire was basically imposed on the forested parts of the catchment. And that bushfire was assumed to have a reduction effect on the initial loss and continuing loss from the catchment. So that scenario, these are the changes in the 1% or the 1 in 100 year design flood estimate at each of the major streamflow gauges, which were used to represent inflows to our hydraulic model, which was the bottom part of the system. And you can see that the increases are very significant. So looking at increases of somewhere between 23 and 67%, with an increase by the time you get down to Lake Wellington at the bottom of the system of 47%. So those are quite large numbers. It is important, though, in a risk context, to point out that those increases really only persist for that first 2 or 3 years post the bushfire. So now I'm going to talk a bit about recent developments and future challenges in this space. The first one, and these are really based on a lot of research that's occurred in recent years. The first one is around the use of alternative means for modelling water yield impacts. So the macaque and the busy models that I mentioned earlier chiefly used leaf area index as the predictor of the change in evapotranspiration from eucalypt forests. Recent research that Dominic Deskerniak and Richard Benyon and others have undertaken has found that sapwood area index can be a much better predictor, and that can be estimated using LiDAR data. So that's offering a lot of promise in terms of an alternative means of modelling, eventually of modelling evapotranspiration and therefore water yield from forested catchments. The second one is really around the response of mixed species eucalypt forests. So the Kazera curve's been around obviously for a long time, several decades now, but it was derived in Melbourne's wetter forested catchments that were largely ash-type forests. Trying to extrapolate that curve to mixed species eucalypt forests is a bit of a challenge, and there's been more recent research that's looked at long-term age studies, paired catchment studies, to try and get a better handle on what the shape of that curve looks like in this mixed species eucalypt forest. The third area, again, this is work that was undertaken at University of Melbourne, is improved algorithms for spatially interpolating precipitation. And that's really about trying to understand, when we've got a bias in where the rainfall gauges are located in the catchment, what does the spatial definition of, what's the spatial pattern of precipitation across the catchment? And that's important for trying to understand how well our model is doing at estimating the evapotranspiration component, which is the difference ultimately between the precipitation and the runoff. So trying to understand how accurately we're modelling evapotranspiration, it's important to understand, well, what is the precipitation going in, and hence what's the difference between that and runoff. The last one's really important, and this is the recognition of the potential for transitions in forest types or forest structures. So the ash-type forests are reseeding eucalypts, and if they get burnt more than twice within a period of about 20 years, there's a loss of the seed bank. If the seed bank isn't artificially replaced, then those ash forests can't reseed. So where we're getting these repeated bushfires over the same terrain, which we have seen in parts of southeastern Australia over the last couple of decades, those wet sclerophyll, those ash forests can't regenerate themselves. And in that situation, we might well see them replaced by other species, such as wattle, acacia type shrublands. If that occurs, there's sort of some interesting, there's obviously a loss of biodiversity and habitat values in that transition. But the weird thing is that from a water yield perspective, it might actually increase the water yield over the long term, because the acacia shrubs don't use as much water typically as a ash type forest. So the important thing to note there is that there's really these three elements that interplay. There are the bushfires, there's climate variability and climate change, which is a significant factor in southeastern Australia, or in all of southern Australia over the last couple of decades. And the last one is timber harvesting, which does occur across many parts of forested catchments in Australia. And all of these interact. So if we look at annual inflows to Melbourne's major dams, the long-term average is shown as the top dashed line there. The reduction, we've seen about an 11% reduction in rainfall since 1997 over Melbourne's water supply catchments. That's translated into about a 30% reduction in mean annual inflow to the dams. And that's caused by some unknown or difficult to tease out interaction between the three factors. So a lot of it is probably caused by that climate variability and climate change component, but there could well be significant interactions with timber harvesting and bushfires, and how those interplay in the future is going to be really important, which is really where my next slide goes. So we've got these factors interplaying on the left-hand side that impact the water yield, and as Peter's pointed out, the impact on the water quality. That then goes into a reservoir and water supply system, which is subject to demands. Those demands are then affected by themselves by climate variability and climate change, by population growth, and also whatever we do around the demand management side, and trying to think about water use in cities as an integrated water management problem with other options to try and augment supply. And the system's also augmented with desalination inputs now. So all of those things have an influence on the security of supply and the water yield. And in my view, in future, we really need to be looking at how that integrated system works together. So future directions, I think there's certainly ways to go around improving models to incorporate new science and data sources. It's important to assess that four bottom line outcome for water supply around economic, social, environmental and cultural impacts, and trying to estimate to incorporate these things in stochastic models. So dealing with all of those uncertainties and interactions between drivers is going to be increasingly important in the future. And that's the end of my talk. Thank you.
Thanks, Philip, for that. That was a really great presentation as well, and we really appreciate you sharing all your knowledge and research of late. So we have a few questions that have come through. We can start with maybe the one that has been upvoted. So Jasmine has got, how would you see the impact of the climate change, a drying climate, on recovery of yield in the long term post-fire?
It's going to vary a lot depending on what catchment you're in and what's going on. So I think it's fair to say that the previous modelling that's been undertaken with MCAC and with BISI is still a reasonable guide to what is likely to happen in terms of the change in water yield over time. But I think it would certainly be good to invest in some models that more explicitly deal with those uncertainties and more explicitly deal with the interactions, as I've said, between climate change, climate variability, recovery of vegetation, and possibly changes in forest structure. So changes in looking at the likelihood that different types of forests might come back to replace what was there before.
Thank you for that. We've got another question here from Charlie. He's asked, can you comment on the difference in results between post-fire yield in mixed forests between FECIMA's 2006 study and the much lower impact from more recent studies by Nolan and Turnbull in mixed forests that suggest close to no yield impact in mixed forest?
I can't comment specifically. I think I would agree that the more recent research is showing that that the mixed species forests, there probably is less impact and the recovery is faster than what the FECIMA et al. Modelling would have shown. Across Melbourne's catchments, yeah, I think that's probably all I'll say, is that it would be good to go back and revisit that. And I think the more recent experimental work is showing different results.
Yep, no worries. Thank you so much for that. Our next upvoted question is from Fiona about groundwater extraction occurs in a big way in the Thompson River catchment. Is this considered, or is it still a small input?
Yeah, it's not explicitly considered in the macaque model, and yeah, so I'd actually need to go back and check to work out how it was considered, if at all.
Yep.
The macaque model is really was mainly used to look at the incremental changes in water yield under a bunch of different scenarios. So it wasn't necessarily used to look at the absolute water yield. It was more to look at if there are changes, for example, in logging scenarios, or if there are future bushfires, what are the outcomes from those? What are the relative outcomes from those different scenarios in terms of runoff changes?
Okay. Thank you for that. Hopefully that's answering everyone's questions, and anything that that you need to take on notice, we can answer later down the track as well. We've got time for one more question before we move on. So we've got Chris has come in here with, are there any plans to conduct some analysis and run these models post 2019 fires in the Murray-Darling Basin?
Well, I think there should be, but I'm not aware of any at the moment.
Yep, no worries. Well, thank you so much, Phillip, for your presentation and sharing your experiences. That's been really helpful and informative. And for everyone listening, we will be following up any remainder questions post the event and sending that out with the recording. So we will aim to achieve answering all of yours that you have during the event.